Hello, my name is Avery Eddins. I'm a master's student at Texas Tech University, and as was just said, I will be talking about radio follow-up of gravitational wave signals from compact mergers with the ngVLA's long baselines. First, I'll give a brief overview. I'll talk about GW 170817, as well as current VLA radio studies related to it, as well as their binary neutron star mergers. And then I will talk about the ngVLA long baseline simulations that we're currently working on, as well as the first results that we've obtained from them. And then I will discuss how the ngVLA-SKA and gravitational wave detectors will work together to help us learn more about compact mergers. So first, GW 170817 was a binary neutron star merger that we detected in 2017 with gravitational wave detectors. It has two main components to its emission. Well, it remains the only event that we've seen in both gravitational waves and electromagnetic waves. And so we were able to get details about its ejecta. And so it has the structured jet and it has the merger ejecta. The structured jet in and of itself has two components as well. It has the fast core and it has the cocoon. The fast core is the cyan cone here, and the cocoon is the blue portion here. The fast core generates the cocoon by shocking the surrounding interstellar medium, which generates synchrotron radiation, which is what we see as the cocoon. GW 170817 had an interesting characteristic in that the jet afterglow was delayed. We did not see emission from the jet until about a week or two later in X-ray and radio, respectively. This is because the jet was initially launched away from us, and then it was very beamed, but as it interacted with the interstellar medium, it started to slow down, and the causal cones, indicated in red up here, started to widen, and that's when we were able to start seeing it because we were finally included in the breadth of the causal cone. And then that's the structured jet. So then we have the merger ejecta, which is in red here, and that is where the kilonova comes from due to the radioactive decay of our process elements. This is why binary neutron star mergers are considered at least one formation channel of heavy elements in the universe. In terms of observing this thing, we first saw the kilonova, then we saw the cocoon from the jet, and then we finally saw the jet afterglow. We are currently using the VLA to look for a kilonova afterglow. I believe this was brought up on Tuesday by James. And this is predicted by our models, but we currently have not observed it yet. On the left here, I have a 3 gigahertz light curve of GW 170817. This first portion is the cocoon, and then as it peaks and falls off, that is how we see the jet afterglow. The points on the graph, the purple and the black and red are 3 gigahertz detections, and the purple is X-ray detections that have been scaled to 3 gigahertz via spectral indices, and you'll see that there's a little bit of an increase right here. You can also see it up here. So that's also motivating our searches that maybe something is in fact there. And then this figure over here is this lower part of the light curve blown up with some kilonova afterglow light curves overlaid. They depend on different mass ratios and equation of state. And so when we detect the kilonova afterglow and how it behaves when we detect it will help us learn about the mass ratio and the equation of state of the initial system. And we are currently taking these observations as we speak, so this is ongoing work. And then another work that we're currently doing with the VLA is a survey of gamma ray bursts that did not have an associated afterglow. This mimics GW 170817 in very early times. So we went to the Swift catalog specifically and found gamma ray bursts that meet these requirements, and then we followed them up with the VLA in hopes that perhaps like GW 170817, they're nearby off-axis mergers that we missed for some reason or another. The typical gamma ray burst follow-up cadence isn't long enough to be able to see the sort of emission that GW 1717 eventually gave off. So we followed these gamma ray bursts of interest up with the VLA, and we checked various things like their morphology, their spectral information, things like that. And we found one candidate that does seem to match the behavior of a binary neutron star merger, at least as far as we can tell from the one follow-up observation we did. And we made light curves assuming a GW170817-like system, as well as by considering the flux that we measured in 6 gigahertz and 3 gigahertz. But you'll notice that there's only one data point here, so we can't say for certain that this definitely came from a binary neutron star merger or anything like that. We need to do follow-up observations to see if it continues tracking with one of our predicted light curves. The ones you see here represent the extremes of the assumption that it's a nearby off-axis merger. So the top one is 40 megaparsecs and the lower one is 200 megaparsecs. So really we can have behavior somewhere in between as well. And so studies like these motivate us to ask the question, how will we conduct such studies in the era of the ngVLA? How can we best use the ngVLA's long baselines to do studies of compact mergers? And so that's what we did. We did some simulations. This is the model that we fed into our Python script, which I'll talk about in a second. And these are the results we got. We have this amplitude versus UV distance plot, as well as this image we got. This plot here shows us that we're at least partially resolving the jet that is in this model here, because as the baselines increase, your resolution gets smaller, you're picking up less flux. As opposed to a point source, if this were point-like, it would just be straight across because you're picking up the same amount of flux no matter what your baseline is. This image here was a simulated 4-hour observation with the main array combined with LBA at 2.4 gigahertz. We think that this fit here that we have is a little bit strange. We're still looking into that, but that's not the point. And so the way we did these simulations is, like I said, we wrote a Python script, but it depends on CASA SimObserve as well as the SM toolkit. With SimObserve, we feed it the model image and we generate essentially a perfect observation. And then with SM toolkit, we add the noise to make it more realistic. The amount of noise we add depends on these equations here. Essentially, the sigma NA depends on the ngVLA performance estimates. It's the expected image RMS for a naturally weighted image. And then we have our chosen number of channels, polarizations. Baselines depends on what arrays we're using, and then we have our number of integrations based on how long we're observing and how long the integration time is. And we're solving for sigma simple. This is the parameter that we feed to SM toolkit to add the noise to our image. However, this equation assumes a natural weighting, and we can't use a natural weighting because if we do that, the long baselines get weighted out and we essentially don't get the resolution that we need. It basically just looks like the main array. So we needed to switch to uniform weighting, and through that we pick up an RMS increase of about 3 times more. This 2.733 figure is from ngVLA memo 55, and we see similar behavior in our own simulations when we switched between natural and uniform weighting. We tested our Python script on data from Corsi et al. 2018 to make sure that we could recover their results. The main difference between their work and our work is that we're working with revision D configuration files and they were using revision B configuration files. Essentially, the difference between ngVLA revision B and revision D, as far as I know, mostly has to do with the main array. So it's not incredibly pertinent to our work, though I hear revision E with some long baseline changes maybe coming up soon. So we were able to recover the results from Corsi et al. 2018. The figure on the left here is from that work, and the figure on the right here is what our script spat out. The scaling isn't exactly right, so this does look a little bit smaller, but really these are the same size within error. We do obtain smaller errors in general with our current script than what Corsi et al. Were able to obtain. We also did some simulations with kilonovae. This is a kilonova at its peak when it's emitting the most. You'll see from this amplitude versus UV distance plot that it is a point source. We're not resolving it, but just because we're not resolving this one doesn't mean that we can't resolve kilonova at all. This happens to be one of our brightest kilonovae, and we've noticed a general trend in our data where the brightest ones also tend to be the smallest ones. So This image is, like the previous one, a 4-hour observation at 2.4 gigahertz with the main array and LBA. And something that we care about a lot is being able to track the centroid, because this will help us deal with model degeneracies that we currently have to contend with the VLA. On this side is the image from the previous slide, and then this is the same kilonova that was simulated at the time that it would have an SNR of about 10, so while still a secure detection. And this red X here indicates the centroid of the kilonova at day 29, and so I'm not sure if you can see the green dot or not, but there's a little bit of a shift that we're able to detect, even though that we're not able to resolve it. And so this is important for modeling. So how will the ngVLA-SKA and gravitational wave detectors work together to help us understand compact mergers? Well, with more and better gravitational wave detectors coming online, their distance horizon will eventually expand beyond what the VLA can see. And so we need the ngVLA's increased sensitivity and resolution to keep up, and SKA as well. In this figure here, Earth is at the center, and as you go further out into the circle, you go to higher redshift. The yellow dots here are where we expect binary neutron star systems to be, and same thing except for binary black hole systems with the white dots. And then the colored contours represent the distance horizons of various gravitational wave detectors. Specifically, the ones of interest that I would like to point out are the pink and green, because that represents Cosmic Explorer and Einstein Telescope. Cosmic Explorer is basically LIGO, but bigger and so more sensitive. It's still an L configuration, but its arms will be 10 times as long. And then Einstein Telescope is a bit more complicated. It's a triangle. And so with the pink and green contours, we can see that we will be able to detect most mergers of binary neutron star systems. And so we need a bigger and better radio telescope to keep up with that. And part of what we're trying to answer right now is how many of these binary neutron star mergers that we will be able to detect in gravitational waves with third generation detectors, how many of them will we be able to do follow-up on in electromagnetic waves with the ngVLA? SKA and ngVLA will work together and have different roles in gravitational wave follow-up. The SKA, with its wider field of view, is better for larger redshifts, because when we have larger redshift, then we'll have bigger localization regions from our gravitational wave detectors. And then with ngVLA, it's better for lower redshift triggers, because we're not dealing with a big localization region, but we may be dealing with an off-axis merger. And so we'd be looking for fainter emission. And so its greater resolution and sensitivity will be useful for that. And then also the ngVLA will be useful for doing frequency coverage. Well, with its wide frequency coverage, will be useful for finding spectral indices, both of low and high redshift triggers. So the ngVLA will enhance current binary neutron star studies as well as enable new ones. And the current degeneracies that we're contending with in our models right now will be resolved through increased resolution. And then we will continue to study how the ngVLA will see binary neutron star emission. We'll explore the optimal settings of how we can best make these observations, as well as develop a public guide. We learned how to do these simulations from a tutorial written by Viviana Rosero, and we're hoping to do something similar, except gear it more towards multi-messenger astronomy, as well as data analysis, to get the information we need that's relevant to such systems. Neutron star black hole mergers are an upcoming topic of study, some future work for us, we hope. And the ngVLA and SKA will uniquely complement both current and upcoming gravitational wave detectors in electromagnetic follow-up. And that's all I have. Thank you.
Very nice talk, and we have some time for questions.
Yeah, very nice talk. So I noticed your simulations were at 2.4 gigahertz.
Yes.
do you consider going to also higher frequencies, exploiting the sensitivity and getting better angular resolution, so improving your constraints on the position?
Yes, we are planning on doing higher frequencies as well. It's just the part of the data set that we've made it through right now is 2.4 gigahertz, but yes, higher frequencies will be included.
Thank you.
Hi, really great talk. This is about your candidate detection. I was wondering if you had searched for a candidate host galaxy near that position, around the same distance that you were assuming.
When we were searching for those candidates, we did have essentially an assumed host galaxy so that we could determine if it was a persistent source or a variable source. But we haven't gone back to specifically be like, okay, yes, this is definitely the host galaxy. So we haven't assumed one, but I think that's future work to make sure that that is securely the host galaxy.
Cool, thank you.
Other questions? Are there any questions on Slack? Let's see, I have a quick question. Avery, I was wondering on the simulation slides that you showed for the kilonova, it wasn't totally clear to me whether it was actually resolved. I didn't see the beam, the PSF on there. Could you remind me what is the linear extent that you expect for the kilonova emission and whether ngVLA will actually resolve it?
It depends on the system. With that specific system that we were simulating, it looks like that we won't be able to resolve it. But like I said, the brighter kilonova tend to be smaller, and so if we can find a balance between the brightness and the size, we will likely be able to resolve some of them. It's just in that particular case, it was not resolved.
All right. Any other questions? All right. Well, if not, that's okay. Let's go ahead and thank Avery again.